The following video will introduce you to freeform optimization using Genesis Structural Optimization for ANSYS Mechanical or GSAM. GSAM is an integrated extension that adds topology, topography, shape, freeform, sizing, and topometry optimization to the ANSYS environment. The extension provides a reliable, robust, and easy-to-use interface which allows designer to set up structural optimization problems, post-processing them, and export the data within the ANSYS environment. Freeform optimization is a special type of shape optimization. It provides a grid-by-grid shape optimization capability in which a given perturbation vector is split to increase the variability of the answers. In the current implementation of GSAM, the freeform optimization is limited to move the surface grids only. GSAM will automatically create perturbation for grids on the selected surfaces. The main advantage of the freeform optimization is that it can produce more variability than the standard shape optimization. Let's start with an example. In this demo, we will use a plate under torsion loads. The objective is to minimize the strain energy to get a stiff structure. I will solve the problem using two different approaches. In the first approach, I will impose three planar symmetric manufacturing constraints along with the grid constraint, whereas in the second, I will impose two symmetric manufacturing constraints and one extrusion constraint along with grid constraint, allowing a pattern to grow in a defined direction. Now open the ANSYS workbench. A static structural solution with three different load cases has already been set up in ANSYS workbench. Now I will switch on the Genesis ACT extension in ANSYS workbench. The Genesis icon will show up in the ANSYS workbench toolbox. Now I will bring the Genesis extension into our workbench simulation so that it shares the existing model information. Drag the Genesis icon in the ANSYS toolbar and drop it on the model cell of load case 3. Now open the ANSYS Mechanical. Make sure that Genesis node shows up in the project tree. Now, in Analysis Settings under Genesis, change the maximum optimization cycles to 25. In Design Methods under Analysis Settings, select Yes for mesh smoothing. This feature is useful when there are shape design variables as the mesh may become distorted. Now, from the Genesis Optimization toolbar, push the Shape Morphing Set button to add a Shape Morphing Set node. Select the two inner faces as the designable region. Now, under Perturbation for perturbation type, in the current implementation of GSAM, only raw morphing set is available. For freeform, make sure that Yes is selected, thus the grids in the shape morphing sets will be designed independently. For perturbation direction, select normal to the surface. For maximum perturbation, enter 1.2 mm. This will allow the grids to move up to 1.2 mm in the defined direction. For edge grid design, select skip edges. It is recommended to pick skip edges if the designable region and non-designable region are not sharing same grids on the edge. For design variable bounds, enter 1 for the upper bound and enter -1 for the lower bound. With this selection, the perturbation can move in both upward and downward direction. Now I will impose manufacturing constraints so that optimization will not lead to non-symmetric part. I will select the local coordinate system whose origin is conveniently located to enforce a symmetric condition. For constraint 1, select mirror about XZ plane. For constraint 2, select mirror about YZ plane. For constraint 3, select mirror about XY plane. For the grid fraction, enter 0.45. Grade fraction controls the fraction of grades in a shape morphing sets that are allowed to be moved in the final design. Grade fraction equal to 0.45 means that 45% of total grades are allowed to be moved. For this problem, I will not use the coarse method, but if desired, you can select the coarse method to reduce the number of design variables. Keep the default values for sensitivity scaling, initial randomness, symmetry tolerance, and grade fraction bound. Now the next step is to define the objective. From Genesis Structural Optimization toolbar, push the objective button. Select the strain energy as the response type. For the load case selection, select all static structural load cases. For goal, make sure that minimization is selected. Now, from the Genesis Structural Optimization toolbar, push the Shape Change Plot button. The shape change plot shows the shape change as displacements from the original shape of each grid. The user can view the deform model simultaneously with the shape change results. Push the Show Deform Model button. Select the shape change as the deform model. Now right-click on Genesis node in the project tree and push Solve. You can check the optimization progress by clicking on Solution Information node. This will take some time, so I will skip the solve time. Now scroll down to check design cycle history. The total number of design cycles are 19. At the end of design cycle 19, value of normalized strain energy is 0.6435. To view the shape change results, click on Shape Change Plot. As you can see from the color bar that the maximum displacement is approximately 1.2 mm, as we have entered the maximum perturbation equal to 1.2 mm. Now we will set the optimization problem imposing extrusion constraints. Go back to ANSYS workbench to add another Genesis system. Open the ANSYS mechanical. Verify that another Genesis node shows up in the project tree. In analysis settings, change the maximum optimization cycles to 25. Now copy the shape morphing set and objective from the first Genesis system. And paste them to second Genesis system. Now click on the shape morphing set. For constraint 1, select extrude along x-axis. For constraint 2, select mirror about xz plane. For constraint 3, select mirror about xy plane. For grid fraction bound, select both. Both is to get a lower and upper bound grid fraction constraint. That is, at least that many grids must move. Keep other parameters same as before. Now push the shape change plot button and show deform model button. In show deform model, select shape change as deform model. Right click on Genesis node and push solve. This will take some time, so I will skip the solve time. Now click on Solution Information node. Scroll down to check design cycle history. The total number of design cycles are 12. At the end of design cycle 12, value of normalized strain energy is 0.7976. To view the shape change results, click on Shape Change Plot. Now we will compare the shape change results obtained in both cases. In both cases, as you can see from the color bar, that maximum displacement is approximately 1.2 mm. As we have entered the maximum perturbation equal to 1.2 mm. In the second case, extrusion constraint is applied along x-axis. Thus grids are moved in such a way that ribs are formed aligning along the x-axis. The table displays values of normalized strain energy for each design cycle in both cases. In first case, the normalized strain energy is reduced by 79%, whereas in the second case, the normalized strain energy is reduced by 73%. Thus, the structure obtained with only symmetry manufacturing constraints is stiffer than structure satisfying the extrusion manufacturing constraints. This completes the demo. I hope that it has helped you to get familiar with implementation of freeform optimization in GSAM. If you would like to learn more, I invite you to check other videos about GSAM. For more information, please visit our website at www.vrand.com or email us at gsam.support@vrand.com. Thanks for watching.